Okay, welcome back. Chapter 5, the wave mechanical version of the atoms. So we said that Bohr came up with this planetary model. The electrons move like planets around the sun, but then they found electrons can't move that way. So the planetary model was out, and they started to focus on what the electrons were doing. They really knew what was going on in the nucleus, but it was difficult to explain what was going on with the electron. So the wave mechanical model is going to focus on the electron. So first, how did we go from Bohr to wave mechanical? Remember, Bohr came up with those emission spectra, and he said that each of those lines represented a possible orbit. But then later technology found that those were not singular lines. Sometimes there were actually multiple lines close together, and Bohr just couldn't see it. So in other words, if we look at the Bohr emission, right, we got our shorter wavelengths like purple and then green and then yellow and then red. So let's label this P, G, Y, and R for the colors. Okay, I guess I could have just wrote out the words purple, green, yellow, and red, but in any event, Bohr said that this was the first energy level, second energy level, third and fourth energy level. And then they found out that the modern view, once we got better technology and you zoom in on this, we find out that yes, the first line really was one line, but the second energy level actually had two lines close together, which meant that there were sublevels to these energy levels. So Bohr came up with the main energy levels. But then later we realized that many of those levels, except for the first one that is, had multiple lines. The third energy level had three lines close together. The fourth energy level had four lines close together. Fifth energy level had five, sixth energy level had six, etc. And that came up with the idea that each of these energy levels had sublevels. So that's the first change. In the meantime, de Broglie said, look, if Einstein and Planck are correct, if a wave can act like a particle, if light can act like a particle, photons, can particles act like waves? And he went out to prove it, and he did. And what he came up with is what's called the wave-particle duality of nature. And as far as the equations go, I mean, they're just combining Einstein and Planck's equation. You don't have to know that. But that de Broglie proved that all things in nature, all things, have both wave characteristics and particle characteristics to them. Now, the smaller and faster something gets, the more we care about its wave mechanics. And the larger and slower something is, the more we care about its particle physics. All right, so first of all, what do we mean by particle physics? I mean Newtonian physics. We care about Newton's three laws. Force equals mass times acceleration, the law of inertia, action and reaction. Those things are important to a large object that is moving slowly. If I was to fall, for instance, I'm considered a cosmically large particle, no comment, and considered cosmically slow. So I'm more concerned with force equals mass times acceleration. What's going to be the impact on my body when I hit the ground? Whereas if you're an electron and you're really small, and you're moving at 80% of the speed of light, we care more about your wave properties. Now, all things have both properties, but the smaller and faster you are, the more we care about your wave properties. So what do we mean by that? All right, well, we already know that light can act like a particle, our solar power calculator. The photons of light hit the solar receptor. That causes electrons in the solar receptor to move, and that creates electricity. So light can act like a particle. Can a particle act like light? And like I said, de Broglie went out and he proved it, that there are properties for particles. They do have refraction, which means that light bends as it changes medium. They do diffract to some extent, which means like sound waves diffract. They bend around corners. And they do reflect. But of course, with a person, we don't care about how much our bodies diffract. Yes, my body, some of it is bending around corners and moving out into the hallway of my office, but such a small amount that we don't care. But for an electron, this is really important. So that was the second change. The duality of nature, wave and particle, that maybe we need to take a look at these electrons and start describing them in terms of wave properties rather than particle properties. In the meantime, scientists in Germany by the name of Heisenberg comes up with the Heisenberg uncertainty principle. Here's the third change from Bohr to the modern atom. That if you are going to figure out the momentum and position of an electron, you can't do both things precisely at the same time. In other words, if you want to find the position of an electron, the best way to do it would be to slow it down. It's a lot easier to locate something when it's moving slowly. Okay, so if you position the electron, you're slowing it down, and now you're messing with its momentum. If you're figuring out the momentum, in other words, how an electron gets from one place to another, then you're not going to know its position because you have to let it go full speed, which is 80% of the speed of light. So what they decided to do was to come up with a compromise. In other words, we can't really slow it down much because then it's not acting like an electron. And because we can't slow it down much, we're not really going to be able to locate it, but we can come up with a pretty good guess. Not going to be precise. It's not going to work every time. But we are going to be able to come up with a guess. Now this guess, these areas called orbitals, I'm going to write that down at this point. Orbitals are these mathematically constructed areas of probability where we might find an electron 90 to 95% of the time. And so Schrödinger came up with the mathematics for this and predicted these little regions. But we have to be careful with these regions, these orbitals. They are man-made constructs. An atom does not look like the orbitals that make up the atom. I'm just going to go here and I'm going to look map of the United States. And of course, my big fat finger hit the wrong button. Really? Okay, so we pick a map of the United States. Let's pick this one. And we can take a look at it and notice that Texas is in yellow and New Jersey's in yellow and Pennsylvania is in sort of a pink fuchsia color. Now, if you go up in an airplane and look down, Pennsylvania is not going to be pink. New York is not going to be purple. New Jersey is not going to be in yellow. It's not going to have little fonts that have the names of the states on them and all that kind of stuff. This is a man-made construct with borders that were based upon geographic and political divisions. It is certainly not how the Earth looks. So it's the same thing with an atom. We can come up with these regions where we can find an electron and we can describe their shapes. But do understand, those are just man-made borders, and they are not going to look like what the atom looks like. So before I show those shapes, what do we actually know about the electrons? Well, we know they move close to 80% of the speed of light. And those mathematical borders that Schrödinger calculated, it seems like the electrons move on the surface of those borders at least 90 to 95% of the time, and then the other 5 to 10% of the time it's doing stuff that we don't understand. Further, we don't know how an electron moves from place to place. What we do know, however, is that the electron is moving so fast that its charge appears to be everywhere on the surface of that orbital at once. And again, I always use the ceiling fan analogy. If you have a fan turned on high, then it looks like one blurry blade. But if you stop the ceiling fan, you can actually see that there's a lot of empty space in between the blades. And to understand, a fan is moving cosmically slow compared to an electron. So Rutherford, when he came up with that sea of electrons model, he wasn't too far off because the electrons were moving fast and the charge did appear to be everywhere all at once. All right, so what are we dealing with? What do you have to know? All right, so first of all, there are these regions called orbitals. And an orbital is an area where you can find 2 electrons. And The hierarchy is we start with energy levels, and then we can divide them up into sublevels, and then we can take the sublevels and come up with different orientations for the sublevels, and then finally we can define the actual orbital where an electron is. For instance, if we're talking about the first energy level, there's only one sublevel called an S sublevel. And S sublevels are spherical in shape, so they only have one orientation in space. I'll get to this in just a moment. So therefore there's only one orbital in the first energy level. In the second energy level, there's what we call an S sublevel and a P sublevel. Now the S sublevel is spherical. It has only one orientation. But the P sublevel, which they call dumbbell shaped, lies along the x-axis, the y-axis, and there's another one that lies along the z-axis, so it has 3 different orientations. So the second energy level holds a total of 4 orbitals. In the third energy level, we now have, besides an S and a P sublevel, we also have what's called a D sublevel. And the D sublevel has 5 different orientations in space. So we have a total of 9 orbitals in the third energy level. And then the fourth energy level, we introduce what's called an F sublevel. And the F sublevel, which is called flower-shaped, has 7 different orientations in space, which means 7 different orbitals. So the fourth energy level actually holds 16 orbitals. Okay. So what do we mean by S shell, P sublevel, D sublevel, F sublevel? I'm glad you asked. There's only 2 that you need to know the shape of. The first is the S sublevel, which we're going to call the S shell. It is spherical. Now the S doesn't come from that. I don't know what the S comes from. But it is spherical in shape. So if we had an S sublevel in the first energy level, we would call it a 1S sublevel. Now the only difference between a 1S and a 2S is the size. In the second energy level, you already have a 1S shell underneath of it, holding electrons. But you also have a 2S shell outside of it. So the only difference between, that is the worst sphere. The only difference between an S shell, wow, and the first energy, that's terrible, and the first energy level and the second energy level is not the shape, but the actual size. The larger the energy level, the larger the size. So as you get further and further away from the nucleus, you can hold more and more electrons because you have more and more space. And as you get further away from the nucleus, your electrons are higher in energy and they have more complicated structures and shapes for their orbitals. Second sublevel, we said, is a P shell. Now a P shell, they say, is dumbbell shaped. So if this is the nucleus, we would have an orbital here connected to an orbital. They would rotate this in 3 dimensions. It's hard to draw. But this would be called a PY shell. A PX shell would be the same shape, dumbbell shaped, but it would be on the x-axis. And then if we had an X and a Y and we drew a third dimensional z-axis, then the third p orbital, is the nucleus, would be called the PZ shell. Now the only difference between a 2p and a 3p shell, again, is the size. So if we go to the third energy level and we were to draw a 3p shell, it would be shaped exactly the same as a 2p shell, but it would be larger in size. Alright, so what does all this mean? What all this means is that we have borders. We have areas where we can locate electrons. We think, maybe, perhaps, we're not sure, because remember, this is just a probability and statistics guess at where the electrons are. But there is a construct to this, that the first energy level only has an S shell. The second energy level has a 2s and a 2p shell. Again, if we were drawing this and we said that this yellow represented the 1s shell, then the green around it would represent the 2s shell. Again, it'd be the same shape, just larger in size. The second energy level also has 3 different p shells: a px, a py, and a pz. Coincidentally, if you put the px, the py, and the pz shells together, they actually make the shape pretty much more or less of a sphere. Now these are the Dshells. And you don't have to know the shapes for the Dshells, but they're named after their orientation in space. This is called the dz squared shell. This is called the dx squared minus y squared, formula for a circle. And then this lies between the x and the z axis, so they call this the dxz shell. And this lies between the y and the z, so they call this the dyz shell. And then this one is the dxy shell. And they say that these are clover-shaped, like a 4-leaf clover. But again, you don't have to know that at this level. And then the last type of subshell is something called an F shell. And the F shell are flower-shaped. Remember in the D shell there was a ring? Well, now we got 2 rings. Remember in the D shell there were 4 of these lobes? Now we got 8. So again, as you get further and further away from the nucleus, we start getting these bizarre shapes, and that has to do with how electrons interfere with each other electromagnetically. It's physics beyond the scope of this class. So again, what do you have to know from this video? Glad you asked. Know that there are different shapes to sublevels, that one, sublevels exist and that there's different shapes to them. The S shell is spherical, the P shell is dumbbell shaped, and the D shell is clover, the F shell is flower shaped. At least that's what they call it. The difference in the shells, again, if this is a 2p shell, then this bigger one is the 3p shell. They're the same shape, just bigger. You have to know that as we move up in sublevels, we get more and more different orientations. There's only one type of S shell, and so that S shell holds 2 electrons. Each orbital holds 2 electrons. Here in the P shell, there is a px, a p, this is pz, and py, and those are going to hold 6 electrons. In the D shell, there's 5 different orbitals, so that holds 10 electrons. And in the F shell, there's 7 different orientations, 7 different orbitals, so that holds 14 electrons. We'll come back to this diagram in the next video. So they love to ask students, hey, in the first energy level, how many electrons fit in the first energy level? Well, in the first energy level, there's only one shell. There's the 1s. Each orbital holds 2 electrons, so there's 2 electrons in the first energy level. In the second energy level, you have an S and a P. So we have a 2s, we have a 2p shell. The p shell has 3 different orbitals, so there's a total of 4 in the second energy level. That means this holds 8 electrons. And then by analogy, we can do it for a third energy level. Now we throw in a D shell, which has 5 orientations. And so there's a total of 9 orbitals for the third energy level, holding 18 electrons. And for the fourth energy level, now we throw in an F shell, 7 different orientations, 7 orbitals. And so there's 16 orbitals total. So the fourth energy level holds 32 electrons. Again, the only difference between orbitals is their shape, and the difference between a 1s and a 2s is its size. The difference between a 2p and a 3p is its size. Notice I didn't say difference between a 1p. There is no 1p shell. There's only one shell in the first energy level, and it's an S shell. And we'll come back to that stuff later. That's it for this video. Thank you very much.